Hi, so this is our application of perfect pulses to improve acoustic and RF underwater wireless communications. So here's a quick introduction on our project. So in order to improve the study of underwater environments, specifically those in oceanic settings, it's necessary for ROVs and AUVs, as well as Ocean Internet of Things devices, to have efficient and robust means of underwater wireless communication. This paper discusses the application of perfect pulses to RF engineering and acoustic communication underwater to allow for higher efficiency modulation and transmission. So here are the three different types of communication methods. There is optical, acoustic, and RF. Optical is most used in short distances, clear water. Acoustic is used because it has a low attenuation, but it has difficulty in shallow areas and is unable to communicate through physical barriers. While RF is used during high frequency selectivity, it's good in short ranges, and it's high data rate communications. On the right, you can see a table, and it talks about shows the comparison of underwater wireless communication technologies, seeing the max range, data range, speed, and power, and how they compare between the three different communication methods. Going into the acoustics in shallow multipath environments, you can see that acoustic communication has relatively low latency and slow bit rates because of the physical properties of sound, so it makes it really difficult for the sound waves to propagate, and you'll see a reflection from the Earth's surface as well as some bottom reflection. So in large distances, it can be difficult to reach the sensor, and it also requires a lot of power to drive compared to other systems. So this multi-path environment with acoustic waves will end up reflecting everywhere and can be difficult for reaching the receiver. And then you have the features of underwater RF and communications, and these are just properties and details about the reliability, performance, and implementation of RF engineering, and how, due to rapid development of higher efficiency antennas, there is more interest in underwater RF applications now, and some key advantages are listed on the slides.
After understanding the current status of research and challenges in underwater communication, this design seeks to use a perfect pulse to modulate incoming signals instead of using a traditional sound wave as frequency carrier. A little bit of background on the perfect pulse. Perfect pulse are binary and typical waveforms that are modulated in frequency and can have either a positive or negative amplitude. This implies that the generating process can be easily done by a combination circuitry of CMOS analog trigger circuit and logic gate. Some fantastic properties of this type of pulses are: first, the generation efficiency is almost 100% and consumes less power than the circuit needed to generate analog signals. Second, it has a strong DC nulling and high frequency roll-off behavior, effectively acting as a high-pass filter when the signal is mixed with noise. DC nulling is also tunable by alternating the length of pulse duration as shown in the next slide. Perfect pulse can modulate the signal using BPSK, PWM, or FSK. Perfect pulse frequency characteristic closely matches the transfer function of electromagnetic wave underwater, so that conjugate matches can allow maximum power transfer. Based on these properties, perfect pulse is a better solution for underwater communication than a sun function. Now we will introduce our method in simulating antennas under seawater. First, we decided to select loop antenna among all types of antennas. We picked it due to its high directivities and magnetic coupling feature. Salt water affects the electric field more than the magnetic field due to its high conductivity. The loop antenna is dominantly magnetic near field. As a result, it will perform better in seawater than any other antenna when picking up signals. Small loop antenna responds more to the magnetic field than a large loop antenna does. And here is the equation to design small loop antenna. Ideally, if the antenna circumference is less than 1/5 of the wavelength, then it is considered as a small loop. If the operating frequency is designed to be 500 kHz, then the antenna circumference has to be less than 90 meters. Our design antenna circumference is around a meter, which satisfies this criteria.
Using these antenna specs that Jay mentioned, we set up a simulation in ANSYS HFSS to simulate signal transmission between two loop antennas. In the picture on the left, we can see the PVC wrapping that is to prevent any surface interactions with the saltwater that decrease the transmission strength. In the picture on the right, we can see the internals of the antenna. In green is the copper conducting part of the antenna. In red is the lumped port of the antenna. This is where the antenna is excited. Not pictured is the radiation boundary set around both antennas. This is filled with salt water and mimics the ocean that we want to simulate. After this model has been set up, we run an analysis. In our analysis, we ran 2 frequency sweeps, one from 1 kHz to 1 MHz with the antenna separated by 1 meter, and another frequency sweep from 1 kHz to 10 MHz with antenna separated by 2 meters. At 1 meter separation, we can see a peak around 500 kHz, while at 2 meters of separation, we can see a peak around 8 MHz. After this, a MATLAB script was created to generate perfect pulses of arbitrary order and time length. Pictured here are the fast Fourier transforms of a P2 perfect pulse and a P8 perfect pulse. As can be seen, the P8 perfect pulse roughly matches the transfer function at 1 meter separation, with a peak around 500 kHz, and the P2 perfect pulse roughly matches the transfer function at 2 meters separation, with a peak at 8 MHz. This means that perfect pulses can be used as rough conjugate matches for transmission underwater. Since a conjugate match provides the maximum power transfer across an RF link, perfect pulses will provide a stronger transmission link than a pure sinusoid at the desired frequency. To conclude our work, we have seen that perfect pulses show promise for being a high efficiency and dynamic method for transmitting RF signals underwater. However, to be implemented in real life, an algorithm must be created to dynamically change the pulse order and time length as the distance between antennas change, as well as the depth of the water. Perfect pulses can also be applied to audio signals, as their usefulness can be extended to the modulation of audio communication systems. They can be used instead of more popular synchronous encoding schemes, which require a faster clock cycle and therefore more power.